All right, let's look at the questions for the checkpoint. So, since this is kind of like your last assessment of these optimization problems, I'm going to work through these a little quicker than I did with the discussion questions and the homework questions. So, we have a curve, parabola y equals minus x squared, which looks roughly like this. I mean, again, these drawings are not supposed to be good or accurate or scale or anything. They're just the only purpose for them is to kind of organize what's happening here. There's also a 0.32, which is not on this curve. So what we'd like to do here, actually, let me exaggerate this a little more. What we'd like to do is to come up with an objective equation or objective function that models the distance between a generic point on this curve and 3, 2. So how do I find the distance from one point to another? I can set this up as a right triangle, figure out what the horizontal distance is, and figure out what this vertical distance is. So let's set up that distance. I'm going to set that up in x and y. What is this horizontal distance going to be? That's going to be, I'll just call this generic point on this curve xy. So that's going to be the distance between x and 3. So I'll just call that the square root of 3 minus x squared. So basically, I'm setting up Pythagorean theorem here. Plus the other distance. So the difference between 2 and y. Plus 2 minus y squared. So I think this is a good objective function in x and y. So what's the constraint here? The constraint function is that, and it's not always like resources that are constrained. It's basically just some requirement you have to fulfill. The requirement here is that, y and x are related in a very specific way. Y is equal to 2 minus x squared. So what I'm going to do here is to insert that and rewrite this. So square root of 3 minus x squared plus 2 minus, what's y? 2 minus x squared. Let's clean this up a little bit. Dx equals the square root of 3 minus x squared plus 2 minus, hold on, that's where it should be. Out here, right? That's gonna make things a little easier. So 2 minus 2 is 0. And then a minus x squared, so plus x squared. One thing I'm going to do here, even though it's totally optional, I'm going to rewrite this as d squared equals 3 minus x squared plus x squared, which is x to the 4th. So this is my objective function in only one variable, and I'm going to differentiate implicitly. So what's the derivative of d squared with respect to x? That's going to be 2d times dd dx. Dx is the thing I'm eventually going to want to set equal to 0. Equals 2 times 3 minus x times -1 for chain rule plus 4x cubed. And I want to set dd dx to 0 because that's where critical points happen when my derivative is equal to 0. So if I set that equal to 0, then the left-hand side becomes 0, and I have 0 equals, let's start cleaning things up. Simplifying, 2 times 3 times -1 is -6. 2 times -x times -1 is 2x plus 4x cubed. So I get 4x cubed plus 2x minus 6 equals 0. So from here, this is a cubic. So what I would encourage you to go to Desmos, figure out what value of x gives you this nearest point. So let me go ahead and do that now. Okay. So pretty clearly, I have an x value of 1. So when x equals 1, what does my y value equal? Equals 2 minus 1 squared, which is also 1. So my point nearest to 3, 2 that is on that curve is 1, 1. All right, moving on to question 2. All right, use calculus to find the area of the rectangle of the largest rectangle. So that tells me that I'm using that superlative language. So the most something or least something, largest area. How do I find the area of a rectangle? Someone's really proud of their engine. So A of x and y equals xy. So length times height here. Actually, it's not quite just xy, is it? So if we're going by, okay, let's go with x and y. We'll start from there. What's the height of this rectangle? It's going to be exactly whatever this y value of this point here is. What's the length of this rectangle? The length is not simply x. It is going to be, one value of x on the right-hand side of the y-axis and one value of x on the left. So that's 2x. So my area is equal to 2xy. What's my constraint? Well, my constraint is that, just like question 1, that y and x are related in a very specific way. So instead of leaving y as is, I'm going to re-express it as 6 minus x squared. And if I expand that, I get 12x minus 2x cubed. I want to find a critical point, so I'll take a derivative. So that's 12 minus 6x squared. Set that equal to 0 and solve. So 6x squared equals 12. That gives me that x squared is equal to 2, or x is equal to plus or minus radical 2. So basically that tells me that actually, I think by the way this diagram is set up, that x can only be a positive value. So I think I have to say that x is equal to radical 2. And I want to find the area, don't I? So if x is equal to radical 2, I can go right back to my objective function. What is the area given that x is radical 2? It is 2 times radical 2 times 6 minus radical 2 squared. So 2 times radical 2 times 6 minus 2, which is 4. I get 8 radical 2. All right, moving on to question 3. We want to construct a cylindrical can on the bottom, no top, okay? It'll have a volume of 30 centimeters. So that tells me, whenever I see these hard constraints like 30 centimeters cubed, that tells me that that's my constraint. So we don't usually figure out what the constraint is before we get the objective function, but that's okay. Let's go ahead and write it down. The volume of our cylindrical can is going to be 30 centimeters cubed. How do I find the volume of a cylinder? That comes from So a cylinder is circular base, so pi r squared times the height. So that's our constraint equation written in terms of r and h. So now what's our objective function? We'll want to minimize the amount of material. So the amount of material, how can we represent that in a mathematical way? That's going to be a surface area. So what's the surface area of this thing? So I have a cylindrical can like this, but basically it's open. So typically the surface area would be, the area of this rectangular side, which will be, so let's say the radius of this thing is r and the height of this thing is h. Then the area in terms of radius and height would be, so this height is, so the area of the rectangle is going to be the height times the circumference of that circle. So that'll be 2 pi r h. And typically you would have to add 2 circular bases to this to get the full surface area. I don't have a top to this, so it's just going to be 1 circle plus pi r squared. So this is the area in terms of radius and height. This is my objective. This is the thing I'm trying to minimize. So how am I going to get this to a single variable? I'm going to use my volume function here to solve for h. So height is equal to 30 over pi r squared. And that allows me to write my surface area in terms of r only. So 2 pi r times 30 over pi r squared plus pi r squared. Do some simplifying. What do I get here? Pi's cancel. This r cancels one of these, so I get 60 over r plus pi r squared. And now I can take a derivative. So this comes out to be negative 60 over r squared plus 2 pi r equals 0. Figure out the fractions. I'm going to multiply the whole equation by r squared. So that gives me negative 60 plus 2 pi r cubed equals 0. 2 pi r cubed equals 60. So r cubed equals 60 over 2 pi, or 30 over pi, which means that our critical r value is the very obvious cube root of 30 over pi. Are we done? I don't know. What are we trying to answer? The dimensions that will minimize the amount of material. So I got one of those dimensions. I need my radius to be the cube root of 30 over pi. So what does that mean the height needs to be? The height is going to be 30 over pi times the radius squared. So 30 over pi, the cube root of that thing squared, so 30 over pi to the 2/3. I suspect that you will want to approximate these values. That's totally fine. I'm going to leave these exact, but yeah, these are the correct dimensions for this. So I need a cylinder with this radius and this height to minimize the surface area and also have the volume that I need. All right, finally, I want to build this pen. Already have a diagram for it. They'll have a fence between them. I have 400 feet of fencing. What dimensions maximize the area of the pen? So what's our objective function? So we want to maximize the area. Right, so let's do this. Are they specified they have to be, so the pens will share a middle fence. That kind of implies to me that these pens are the same exact size, but I'm saying that's a middle fence. So let's do this. Let's say these horizontal line segments are X's and these vertical line segments are Y's. If that's the case, then what's my objective function looks like? What is the area of this whole configuration? the length is going to be 2x, and the height or the width is going to be y. So that's my objective function. What is the constraint? The constraint is going to come from how much fencing I have. So I have to build, I'll call it perimeter, even though it's not strictly speaking a perimeter. Maybe I'll just call it length. Fireworks are going off. So this length here is equal to, how many y segments do I have? I have 3 y segments and I have 4 x segments. So 4x plus 3y, that's equal to what? 400 total feet of fencing. So I need to combine these. So I don't think it matters which one we choose. Let's just choose to solve for y. So 3y equals 400 minus 4x, which means that y equals 400 thirds minus 4 thirds x. So that gives me a way to write the objective function in terms of x only. So 2x times y, which is 400 thirds minus 4 thirds x. Or if we simplify, we get 800 over 3x minus 8 over 3x squared. So that's my objective function. In order to find a critical value, we should take a derivative. So we get 800 thirds, that should be a 3, minus 16 thirds x, and I want to set that equal to 0. So finally, 16 thirds x equals 800 thirds, or 16x equals 800. I believe that comes out to be finally a nice even number. X equals 50. I'm just going to be paranoid. I believe 16 times 5 is 80. Yep. So 50. So what are we asked exactly? What dimensions maximize the area? Okay. Well, one of those dimensions is 50. So what's the y value that goes with that? So y equals 400 thirds minus 4 thirds times 50, which will be 400 thirds minus 200 thirds, or all told 200 thirds. So 50 feet by 200 over 3 feet. So those are the dimensions that give us the maximum area of this configuration.